You're about to witness Bernoulli's principle in action, specifically how a fluid changes pressure when forced through a pipe of varying cross-sections, and we're going to do it without flooding your laboratory station. Over the next 5 minutes, you'll learn the proper physical setup of the FM24 unit, how to completely purge the system of air bubbles, and the methodical steps required to collect valid pressure data. You only need 4 things for this experiment: the FM24 demonstration unit, a hydraulic bench filled to 90% capacity, a standard stopwatch, and a small screwdriver. Gathering accurate data in this lab relies entirely on executing the physical setup perfectly. If we skip steps now, we'll spend hours chasing phantom errors in our math later. Step 1 is getting the hardware in place. Start by locating the FM24 apparatus on the flat top of the hydraulic bench. Attach a spirit level directly to the baseboard. Adjust the 4 leveling feet until the baseboard is perfectly flat, and verify the test section union joints are hand-tight. Next, connect the flexible inlet tube to the bench and secure the outlet hose into the channel. Leveling the unit establishes a true 0 for the elevation head, meaning our Z value is 0 across the entire pipe. This ensures gravity doesn't skew our pressure readings along the horizontal plane. Now we introduce water. First, partially open the outlet flow control valve on the Bernoulli unit. Then, make sure the main flow control valve on the hydraulic bench is fully closed. Switch on the pump. Gradually open the bench valve to allow the piping to slowly fill with water. Watch the clear acrylic test section. You are looking for visual confirmation of water flowing steadily into the Venturi tube and discharging neatly into the collection tank. This gradual priming process prevents water hammering. A sudden spike in pressure could easily rupture or damage the delicate acrylic Venturi meter. Take a close look at all the glass manometer tubes and plastic transfer lines. You are checking for trapped air bubbles. As this diagram shows, an air bubble breaks the continuous column of fluid and displaces the water volume. To remove them, take your screwdriver and locate the air bleed screw at the top right side of the manometer board. Press this valve lightly. If you push too hard, high-pressure fluid and trapped air will spray out and wet you or the lab space. Allow sufficient time for all the bubbles to escape. You can also use this bleed valve to adjust the overall water level in the manometer tubes if the readings go too high or drop out of sight. Trapped air invalidates the experiment. Compressible air bubbles destroy the fluid continuity required to measure static pressure accurately. With a bubble-free system, proceed to increase the water flow rate from the bench until the flow in the pipe stabilizes. Slowly close the discharge valve on the unit to reduce the flow slightly, dialing in the maximum measurable flow rate on your manometers. Grab your stopwatch. Measure the time it takes for the water level to rise in the volumetric tank to calculate your actual average flow rate. Locking in this steady baseline flow is the only way to ensure the mean velocity remains constant while we take our pressure readings. Now we collect the data. Gently slide the hypodermic probe until its tip aligns with the first cross-section of the Venturi tube, labeled cross-section A. Directorial: never pull the total pressure probe fully out of its downstream guide, or you will break the seal and cause a leak. This diagram illustrates what we're measuring. Give the water levels time to stabilize, then note the reading on manometer G. Because the hypodermic tube forces the fluid to a dead stop, manometer G measures the total head, or stagnation head. At the exact same time, record the reading on manometer A. This tube connects to a wall tap that doesn't obstruct the flow, so it measures just the static head. Slide the probe carefully to sections B through F, recording both manometer G and the corresponding static manometer at each point. Once you finish the pipe, regulate the discharge valve to create a lower flow rate, and repeat the entire process for 3 decreasing flow rates. Capturing both the total and static heads simultaneously allows you to mathematically isolate the exact velocity head at each unique constriction in the pipe. When testing is complete, close the water supply and valves, turn off the pump, and drain the water. This table shows what your final collected dataset should look like, with clear paired readings for total head and static head across all 6 cross-sections. This graphic shows your next step. You will plug your head measurements into Bernoulli's equation to calculate the fluid's velocity at each section. Then you will check those results against the theoretical velocity calculated using the continuity equation and your average flow rate. Conclude that if the setup was perfectly level and completely purged of bubbles, these two mathematical models will align. This verifies the physical principle. As fluid velocity increases through a constriction, static pressure must decrease to conserve the system's total energy.